Welcome. In this video, we'll be taking a look at what are called arithmetic sequences. So these are just a special type of sequence. So without further ado, we'll go ahead and define these. So we say that a sequence is arithmetic if the consecutive terms share a common difference, which we call d. And what this means is that as we're going from one term to the next, we're just adding the same value every single time. So if we look at some examples of arithmetic sequences, we might have something like the following. Suppose we say a sub n is equal to 4, 7, 10, 13, 16, and so on and so on. And so hopefully it's not too difficult to tell that as we go from one term to the next here, we just keep adding 3. So that makes this an arithmetic sequence. And what we're saying there is that the common difference of the terms is 3. So this is what is meant by an arithmetic sequence. If we look at some other examples here, we might see something like a sub n is equal to 1, 3 over 2, 2, 5 over 2, 3, 7 over 2, and so on and so on. So this would be another arithmetic sequence. In this case, the common difference would be 1/2. And we can even have an arithmetic sequence in which the common difference is negative. So for instance, I might have the sequence 4, 3, 2, 1, 0, -1, and so on and so on. And there we can see that the common difference of the terms would be -1. So this is all we're talking about when we're discussing arithmetic sequences. It's just one where as we go from one term to the next, we keep adding the same value every single time. And the value that we're adding can be negative, so it can be thought of as subtracting the same number over and over. And so arithmetic sequences are nice because they have very simple formulas to work with. So if we assume that a sub n is arithmetic, then how do we find a formula for the terms? Well, that's what we'll take a look at here. So we would start with the first term, which of course we would denote by a sub 1. For the next term, a sub 2, we would simply take that first term and add the common difference to it. So a sub 2 is just a sub 1 plus d. For the third term, a sub 3, we could think of it as taking a sub 2 plus d, but we want to keep things in terms of a sub 1. So the way I'm going to write this is we're just going to take the last term, a sub 1 plus d, and then you would simply add d again. And of course we could write this as a sub 1 plus 2d. And so if we just keep adding d onto the previous term every time, then for a sub 4, you would have a sub 1 plus 3d. For a sub 5, we would have a sub 1 plus 4d, and so on and so on. And so if we continue with this pattern, then when we want to find a sub n, we would start with a sub 1. We would add on to that n minus 1 times d. So notice that the coefficient of d is always 1 less than the term that you're on. So when we go back and look at the fifth term, we can see that the coefficient of d is 4. For the fourth term, the coefficient of d was 3, and so on and so on. So the coefficient of d is always 1 less than the term that we're looking at. So this is the formula that we're going to be using for working with arithmetic sequences throughout the remainder of this section and this chapter. So let's go back and look at a couple of the examples that we considered already. So we saw a moment ago that the sequence here was arithmetic with a common difference d equal to 3. And so what we're going to do here is we're going to find a formula, or an explicit expression, as it's also called, for the sequence, for a sub n. And so what that means is we just want to come up with an equation in terms of n that could be used to find any term in this sequence. So since we've already decided that it's arithmetic, then that means that we can use our formula here, a sub 1 plus n minus 1 times d. And so we simply have to plug the information in. So we can see that the first term, of course, is 4. Just looking at the terms as they're listed, very first one, of course, is 4. So I plug that in for a sub 1. And then we'll have n minus 1 times d. Well, d, we pointed out a moment ago, was 3. Now we don't want to leave our expression like this. We do want to simplify it. So that means that we'll distribute the 3 here to give us 3n minus 3. And then adding the 4 to that, this will simplify to 3n plus 1. And so that would be our expression for a sub n in this case. And you could confirm this just by plugging in a few values. Notice that if we plug in n equals 1, we get 4. When we plug in n equals 2, we get 7. When we plug in n equals 3, we get 10, which is exactly the terms that we're seeing in the original list of terms for the sequence. So it's very easy to check that we're getting the right answer. So let's do the same thing for one of the other examples we looked at a moment ago. So we had the sequence 4, 3, 2, 1, 0, -1, etc., etc. And again, as we pointed out earlier, we said that the common difference here was -1. So again, starting with my formula for arithmetic sequences, I can just plug in my information. So in this case, a sub 1 is 4. And we'd have plus n minus 1 times our common difference we said was -1. And again, we want to distribute to simplify this. So this will become 4 minus n plus 1. And we can just simplify that to 5 minus n, or you could also write it as -n plus 5. Either one would be fine. But that would be our expression for a sub n in this case. And again, it would be very easy to check to make sure that we have the right answer. Just plug in the natural numbers 1, 2, 3, 4, and so on, and you'll get precisely the list that we see at the beginning of the problem. So what I would like us to notice for each of these examples here is that for the previous one, we said that a sub n was equal to 3n plus 1. And remember that we said that the common difference there was 3. And for this other one that we just looked at here, we have 5 minus n, or as I said a moment ago, you could also think of it as -n plus 5, but the common difference there was -1. Well, notice that the common difference always is the number that we're multiplying by n, and that happens every single time. In fact, when you look at the expression for an arithmetic sequence, it's going to be a linear expression in terms of n. This is an important fact to remember. What we say is that if a sub n is arithmetic, then its formula will be a linear expression in terms of n. The coefficient of n will be the common difference d. And so again, when we say a linear expression, that just means that if we were to graph the equation, it would just look like a straight line. So you can think of it in terms of slope and y-intercept if you want. But we just want to recognize when we have an arithmetic sequence and when we do not. So if we look at some examples here, let's try to answer, is it arithmetic or not? So it's important to realize here that not all sequences are arithmetic. This is just a special type of sequence that has this property of adding the same number every time, but there are certainly plenty of sequences out there that are not arithmetic. At any rate, suppose we had the sequence, let's say a sub n is equal to, how about 2n minus 10? So if you want to, in order to recognize whether or not it's linear, you can think of this in terms of ordinary x, y notation. Just thinking of the a sub n as y and replacing the n with x, we could also think of this equation as y equals 2x minus 10. And so you really just want to ask yourself, is that a linear equation? If you were to graph that, would you get a line? And sure enough, yes, it is. It's in the form y equals mx plus b. It would have a slope of 2 and a y-intercept of -10. But that means that this expression here is arithmetic. We do have an arithmetic sequence here, and in fact we could say that the common difference here would be 2. Remember, the common difference d is always going to be the coefficient of n. So if I were to list out the terms here one by one, I would see that I'm increasing them by 2 as I go from one term to the next every time. And I'll let you plug in some numbers there to confirm that on your own. So let's try another example here. What if I have the expression a sub n is equal to, let's say, n squared plus 1? Well, again, if you want to think of this in terms of x, y notation, this would be the same thing as writing y equals x squared plus 1. So is that a linear equation? When we graph that, do we get a line? And hopefully by now you know that this graph would be a parabola, certainly not a line. So no, this is not linear, therefore it is not arithmetic. take a look at one more example here. Suppose we have a sub n is equal to, let's say, negative 1/3 n plus 18. Well, again, think of it in terms of x and y notation. If you write it as y equals negative 1/3 x plus 18, is that a linear equation? And yes, it is. And here we would know that the common difference of the terms would be negative 1/3. Again, the coefficient of n is always going to be the common difference d when we know that the sequence is arithmetic. Okay, the next thing we'll look at here is how we find specific terms in a sequence when we're given other terms. So a typical kind of example of working with arithmetic sequences is, first of all, if a sub n is arithmetic, suppose we have the following information. Let's say we know that the sixth term, which of course we could denote as a sub 6, suppose we're given that that's equal to negative 34. And suppose we also know that the 11th term, so we'll call this a sub 11, is equal to negative 64. What we're going to do here is we're going to find the 101st term of this sequence, or a sub 101 if you prefer. So how would we do that when we are given two specific terms in the sequence? Well, what we want to do is basically to create a system of equations. What we know is that for the sixth term, a sub 6, we know that that's equal to negative 34. But from our formula, a sub 1 plus n minus 1 times d, I know that this would become a sub 1 plus, we would have 6 minus 1 times d. Or in other words, this would simplify to negative 34 is equal to a sub 1 plus 5d. So again, this is just going back to our formula for the arithmetic sequences. I'm simply plugging the 6 in for n. Okay, well we can do the same thing for the 11th term. A sub 11 we know is negative 64, and so that would have to be equal to a sub 1 plus 11 minus 1 times d. And so this would simplify to negative 64 is equal to a sub 1 plus 10d. Well, what I can do now is to take these two equations that I've just found, the negative 34 equals a sub 1 plus 5d, and negative 64 equals a sub 1 plus 10d, and create a system. And so I'll label these as R1 and R2, just as we've done in previous examples. So we'll write R1 is negative 34 equals a sub 1 plus 5d. And actually what I'm going to do here is to subtract R2. Let me go ahead and put the minus sign in front there. And so I'll distribute the negative to the R2 values. So that would give us 64 is equal to negative A1 minus 10d. And I do this, I'm just using elimination like we've seen in previous sections, in order to cancel the A1 terms. And so what we'll get here is 30 is equal to negative 5d. So we can solve for d very easily here to find that it's equal to negative 6. So that's our common difference in the terms here. Now ultimately we're trying to find the 101st term in the sequence, so we need to plug this back in order to figure out what A1 is. So I can take the common difference here and plug it into either one of my equations, R1 or R2. Doesn't matter which one. I'll go ahead and plug this into R1. So we have negative 34 is equal to A1 plus 5d, so that's 5 times negative 6. Whoops, sorry, negative 34, so a sub 1 minus 30. Anyway, so we should get that a sub 1 is equal to negative 4. All right, so for the 101st term, if I plug that into my formula, I'm going to have a sub 1 plus 101 minus 1 times d. So a sub 1 we've just found is negative 4, so this would become 100 times d, and we said earlier that d was negative 6. And so what I should get here is negative 604 for my 101st term in this sequence. So when you're given two terms in a sequence and you're asked to find another term, You simply need to solve the equation of the sequence, basically, by setting up a system of equations, just as we did in this example. And once you know a sub 1 and d, then you basically know everything you need to know about the sequence. If you have those two pieces of information, then you can find any term in the sequence that you want. So let's try one more example like that. So again, assuming that a sub n is arithmetic, suppose we know this time that the sixth term, a sub 6, is equal to 12. And suppose this time we're given the 14th term of the sequence. So suppose we're told that a sub 14 is equal to 28. Well, again, let's find the 101st term in this sequence. So let's find a sub 101, just like we did in the previous example. Again, I could find any term in the sequence, but just go with the 101st term on these examples. Anyway, so just as before, for a sub 6, we know that's equal to 12, and so that would have to be equal to a sub 1 plus, again, it's 6 minus 1 times d. Or this would simplify to just a sub 1 plus 5d. And for the 14th term, we know that that's 28. And that's going to be a sub 1 plus 14 minus 1 times d. And this, of course, would simplify to 28 equals a sub 1 plus 13d. And so again, this allows me to create a system of equations. So I'll label these as R1 and R2. And just like in the last example, I'm going to end up subtracting these two equations. So R1 is the 12 equals a sub 1 plus 5d equation. Then we're going to subtract R2. So I'm subtracting the second equation that I have here. So if I distribute the negative to all those terms, then we just want to add them like we normally do. And so the A1s will cancel. What we should have here is negative 16 is equal to negative 8d. And so in this case, we get that d is equal to 2. Once again, I can find my first term by plugging this value for d back into one of the original equations. I'll go ahead and use R1 here. So we'll have 12 is equal to a1 plus 5d, so that's 5 times 2. So we have 12 is equal to a sub 1 plus 10. And so in this case, a sub 1 is also 2. And so as before, we want to find the 101st term of this sequence. So again, the 101st term, that would be a sub 1 plus 101 minus 1 times d. So a sub 1 we know is 2, and this will become 100 times d. So that's 100 times 2, since d is also 2. And so we should end up with 202 as our result. So hopefully working with these arithmetic sequences is fairly straightforward. We're just working with linear equations, basically, and systems of linear equations in order to find specific terms in these types of sequences.